Hello and welcome to Physics Platter. This is the second class on sound. In the previous class we have discussed about some characteristics of sound waves. We have talked about the wavelengths, frequency, amplitude, time period, their symbols and their SI units. Like wavelength is symbolized as lambda, the SI unit is m, meter, frequency which is symbolized as nu or f, you can also write it as f, and the SI unit is hertz or per second. The amplitude is represented as A and the SI unit is meter, m. Time period, capital T, and the SI unit is second. Alright. Today in this lecture we will be talking about the speed of light, the relation between the speed and this the wave, the nature of the waves, the characteristics of the wave. Then we will talk about the reflection of light, reflection of sound, and then some applications of the reflection. Alright. So let's start with the speed of sound. Speed of sound. We know that the wavelength lambda is defined as the distance traveled by the wave or the sound wave for a complete vibration of the vibrating particle. Alright, and that complete vibration takes time t, that's the time period, right? That means in time t seconds the wave goes lambda meter, a distance of lambda meter. Alright, a complete wave that takes time t. Therefore, in 1 second the wave would go lambda by t meter, and that's the definition of velocity, right? Velocity is defined as the distance or displacement traveled by the wave in 1 second, right? So this is our velocity, actually velocity of the wave. Therefore we can write v equals to lambda by t equals to lambda into 1 by t. Okay, now we know that the frequency nu equals to 1 by t, alright, or f equals to 1 by t. Therefore you can write this equals to lambda into nu. Therefore the final equation becomes v equals to nu lambda, alright, or lambda by t. That's our final equation for the velocity of a wave. Alright, in this case the sound wave. The velocity of sound at 0 degree centigrade temperature through the dry air in the normal pressure, which is 76 centimeter of mercury pressure, the velocity of sound is given as 332 meter per second. Okay, now why did you mention the temperature and pressure? Because the velocity of sound depends on the temperature. Well, how does it depend? It depends on, it is actually the velocity of sound is directly proportional to the root of the absolute temperature. Here capital T is absolute temperature, mind it, alright. So T is basically absolute temperature, represented as T, and the SI unit is Kelvin, of course. Alright, so velocity of sound is directly proportional to the square root of the absolute temperature. That means if the temperature increases, the velocity of sound also increases through air. Velocity of sound does not depend on pressure. Mind it. Velocity of sound does not depend on pressure, but velocity of sound depends on the humidity of the air. If the humidity increases, the velocity also increases. When the humidity of the air increases, the velocity also increases. Alright, so these are the relations between the different properties of the medium and the velocity of sound. Okay, now of course we have mentioned in the previous class also that velocity of sound in solid is greater than velocity of sound in liquid is greater than velocity of sound in gas. Alright, so velocity of sound in solid is maximum, alright, velocity of sound in liquid is moderate, and velocity of sound in gas is less, which is, we have said that At 0 degree centigrade temperature through the dry air, it's 332 meters per second. Okay, now velocity of sound, this velocity of sound which is 332 meter per second through dry air or in the sea level is known as the sonic velocity or sonic motion. It is known as the sonic motion. Okay, any velocity which is more than 332 meter per second through air is known as the supersonic velocity or supersonic motion. Like we know that some of the warplanes are supersonic, right? They have even higher velocity, and typically it is actually at 20 degree Celsius temperature, and at sea level is around 343.2 meter per second, which is approximately 1236 kilometer per hour. Okay, so that's the supersonic velocity, supersonic motion in the dry air in sea level at 20 degrees Celsius temperature. That's a typical value of the supersonic motion. Alright, remember one thing, to produce sound we need a vibration, right? Without vibration the sound cannot be produced. Now, can all the vibrations produce sound? Of course it can, but we cannot hear all the vibrations. Okay, we can hear only the vibration between 20 Hz to 20 kilohertz or 20 Hz to 20,000 Hz. That's only the audible range, range of vibration that produces sound, and our ear and brain can recognize this sound. Okay, any vibration, and this is called the sonic vibration. Okay, therefore audible vibration which is 20 Hz to which is in the range of 20 Hz to 20 kilohertz is called the sonic vibration or audible vibration. Alright, any vibration below 20 Hz is called the infrasonic vibration. Okay, and of course this is not audible or not recognizable by the human ears. Alright, and any vibration, this is the infrasonic, any vibration that is more than 20 kilohertz, that is also non-audible and called ultrasonic vibration, and that is also non-audible. Alright, any vibration below 20 Hz is infrasonic, non-audible. Any vibration below 20 kilohertz, above 20 kilohertz is ultrasonic, of course that is also non-audible. Okay, although these are non-audible vibrations, still we have some applications of these vibrations, especially the ultrasonic vibration. From the name itself you can recognize the use, right? For example, what are the use? Few examples, there are few uses that human do or we apply ultrasonic vibrations are like, for example, this is used to find the depth of the sea, or ocean, or height of the aeroplanes in a device that's called sonar. Sound and navigation ranging. Alright, we will talk about this in detail in few minutes. Depth of ocean or height of an aeroplane we can measure with the device sonar, sound navigation and ranging device. Alright, and then again we can also with the help of the sonar we can also recognize the presence of some big stones, icebergs maybe, or maybe the submarines and something like that. Alright, and then ultrasound or ultrasonic vibration is used in ultrasonic ultrasonography. We all know what it is. It's a way of studying some of the human organs inside the body. We use the ultrasound or ultrasonic waves to recognize some of the body structures of some of the human organs. Alright, that's called the ultrasonography. Okay, and these are the few examples of the application of the ultrasound by human beings. And then also there are some animals that use ultrasonic waves. For example, bats. Some bats use them to recognize their prey. Okay, to follow their prey. They apply these ultrasonic waves to find the distance and speed of some insects that they eat. Alright, and then inside the ocean there are dolphins and some sharks use ultrasonic waves to communicate among themselves. Alright, so these are the uses of the ultrasonic waves. Alright, now because sound is a wave, it can get reflected. So let's talk about the reflection of sound wave. Because sound is a wave, it gets reflected. Now because sound wave is much bigger than the light wave, it needs a very big reflector, very big and hard reflector. Alright, but then the reflection of sound follows the laws of reflection. Okay, so it also follows the laws of reflection. We know that just like light. Alright, we know that there are two laws. If there is a wave coming, incident wave AO, let's say, it can be sound wave coming and falls on a surface which is in this case hard and very large, and then gets reflected by it, and this is, let's say, is the reflected wave. And if we draw a normal on this point of impact O and then name it ON, this is an imaginary line, of course, normal to the surface of reflection, then AO is a incident wave, OB is a reflected wave, then we know that, and this is also angle of incidence and this is the angle of reflection. Then laws of reflection says that the angle of incidence equals to angle of reflection. And then number 2, it says that the incident ray or incident wave, the reflected wave OB and the normal drawn on the point of impact on the reflecting surface all lie in the same plane, all lie on the same plane. So these are the laws of reflection that are followed by the sound wave also, just like the light wave. Alright, just in this case, because the sound wave has very big wavelength, the reflector must be very big compared to the light and hard. Okay, so these are the reflections of wave, sound wave. Of course, there are some, because of the reflection we know that a echo is produced. Echo is produced. What is echo? We can hear the echo when we go to the, especially to a hilly area or a very empty space with big walls. Let's say if we make very high sound, then we can hear the echo or the reflection of the sound comes to our ear after some times, right? So echo is the sound, the reflected sound that comes to our ear after the original one, after it gets reflected from a hard and distant reflector. That's an echo. Okay, the properties of echo must be, we can say that the echo has to be very clear. Whatever we hear, it must be very clear, and it is, of course, the very faint also, if not very, but of course fainter than the original one. Alright, because it has much less energy than the original one, because we can hear it after it travels some distance and then it gets reflected by reflector and then comes back to our ear. Okay, and then the reflector, to produce echo, the reflector has to be some distant apart from us. Okay, if it's very nearby, we cannot hear the echo. Okay, so clear what is echo? Echo is a reflected sound that comes to our ear after the original one, after the sound gets reflected from a distant heard object or reflector. Okay. Alright, now even if the sound wave gets reflected by everything, we cannot hear echo all the time, right? Because even now I am talking, and then because I am producing the sound wave, this wave can get reflected by everything around me, because there are so many hard things around me like the walls and the furnitures, right? But I don't hear the echo here. Why? Because to produce echo, the reflector must be some distant apart from our ear. But how much distant apart? There is a minimum distance of the reflector from our ear. What is that minimum distance? Okay, to know the minimum distance, we have to know something which is called the persistence of sound. But let me talk about the persistence of sound first. Persistence of sound. What is that? When we hear something, remember one thing, our brain cannot recognize two sounds at the same time. Alright, they must be some time apart from each other. How much is that? When our brain recognizes a sound, remember that sound remains in our brain or persists in our brain for 1/10 of a second or 0.1 second. Whenever our brain recognizes a sound, that sound persists in our brain for 0.1 seconds. That means we cannot hear any other sound if it comes within 0.1 second. So the sound has to reach our brain after 0.1 second to be recognized. Alright. Therefore, the echo that comes to our ear, the first echo that comes to our ear must be coming to our ear after 0.1 second of the original one. Okay, so let's say this is our ear, let's say, and then the sound goes, let's say the source is somewhere here also, and then the sound goes, and then there is a reflector here, gets reflected, the sound goes all the way and gets reflected and comes back to our ear. Alright, now we hear this original sound, let's say, and then after we hear this is original sound, let's say, after we hear the original sound, the echo must reach our ear after 0.1 second. Alright, that means in 0.1 second the sound must travel all the way to the reflector and come back to our ear. So how much distance is that? In 1 second we know the velocity of sound is 332 meter per second. Alright, therefore that means that sound travels 332 meters in 1 second, right? Therefore in 0.1 second the sound must travel a distance of 332 into 0.1 meter, that is 332 into 1 by 10 meter, which is equal to 33.2 meter, and this is the total distance traveled by the sound before it hits our ear. Okay, the echo. Alright, in this distance is the distance that the sound traveled all the way to the reflector and came back. That means what is the distance of the reflector from our ear? Half of this. Alright, therefore the minimum distance, and that is the minimum distance required, minimum distance of the reflector to produce echo is 33.2 by 2 meters, half of that is equals to 16.6 meter, which approximately we can say 17 meters. Alright, so that's the minimum distance of the reflector, that must be the minimum distance of the reflector from the ear. If the reflector remains within stays within this range, we cannot hear the echo of the sound. Alright, that's clear. Okay, now if we stay in a big hall room, let's say, if we stay within a very big hall room, we can hear that whatever voice we make, whatever sound we make, that persists for some times. Although we cannot hear the clear echo, but that sound persists for some time. It it is not so clear, but it somehow gets extended, and that is called the reverberation. Reverberation. Remember that whatever we hear in the empty hall or big hall room, that's not an echo, but that's a reverberation. Okay, because the echo, the reflected sound comes to our ear very soon after the original one, that the original ones, they overlap actually. Alright, so they overlap with each other. That means the edges are not so clear, but somehow the sounds like a little bit extended one, and that's called the reverberation. Alright, okay, now we will talk about some of the applications of the echo, and that is sonar. We will specially talk about sonar now, as I have told you. The full form of sonar is sound navigation and ranging. Sound navigation and ranging. Sonar is a device in which a source of sound is there, especially ultrasonic vibration, and there is a receiver. Okay, with the help of the sonar we can recognize, or we can measure the depth of sea, depth of ocean, let's say, depth of ocean, and then height of some aeroplane, or also we can recognize the presence of some big devices inside the ocean also, like submarines or big stones, or big, let's say, what can I say, iceberg. Okay, and these are very important, right, for a ship to proceed. Okay, so these are the things we can do with the sonar, sound navigation and ranging. How can we do that? First of all, it's very easy. For, let's say, this is the water surface in the ocean, and there is a ship here. Okay, so what it does, this is the bottom of the ocean. There is, as I told you, there is a source of the sound, and there is a receiver of sound. The source produces ultrasonic wave that goes all the way to the bottom and gets reflected and then comes back. Okay, and then the receiver receives that signal. Okay, and then this distance is very, very small, of course, compared to the depth of the ocean. Therefore, we can say that if the velocity of sound is v, then let's say the time it takes after the source releases the signal, the receiver receives after time t seconds, let's say, receives the signal. Then, of course, this is h if the depth is d or h, let's say d here. Therefore, d should be how much? Velocity of sound traveled in t second divided by 2, because it went all the way to back and then came back. So that is the depth of, that must be in meter or kilometer, whatever. So that is the depth of the ocean. Very easy. Okay. Now, how can we measure the height of an aeroplane? Let's say an aeroplane is moving with velocity capital V. Okay, or let's say velocity, the aeroplane is moving with VA. Okay, the velocity of the aeroplane is VA, let's say. Let's say again the source S, at point S, the source releases the signal this is the ground, the source releases the signal at S and then it gets reflected by the ground, and then at point R, let's say this is point R because there is the receiver here, the plane receives the signal, alright, after time t seconds, alright. See here, let's say velocity of the aeroplane is Va and velocity of sound is Vs in this case, alright. Let's say this is S, this is O, and then let's draw a normal here and let's name it as N. Remember that we cannot ignore the distance SR in this case because the velocity of aeroplane is not negligible compared to the velocity of sound. Okay, that's why we have to consider this distance as well. Okay, in this case, after time t, the aeroplane receives the signal. Alright, so in time t, the aeroplane moves how much distance? In time t, the aeroplane moves the distance SR, which is equals to, we can say, Sn plus Nr, right? Sn plus Nr. Therefore, Sr is how much? Sr equals to velocity of the aeroplane into time t. Okay. Alright. Similarly, the sound wave goes all the way through SO and then again travels OR and then gets received by the aeroplane, the receiver, and in this much distance is traveled by the sound in time t. Therefore, the distance traveled by the sound wave is how much? SO plus OR, alright, equals to, what is the distance here? Velocity of sound into time t. Okay, therefore, SO is how much? SO we can say, because SO equals to OR, same distance. Similarly, here we can, here SR equals to this and SN equals to NR in this case, right? Okay, therefore, SO equals to OR. SO equals to OR is how much? Equals to VST by 2. Okay. Now, if we consider the right angle triangle, let's say SON, if we consider the right angle triangle SON, we know that the hypotenuse square equals to the base square and the height square, right, which we can say that height, let's say the height is h here, therefore we can say h square equals to the hypotenuse square, which is SO square minus SN square, right. Therefore, we can say h square equals to SO is Vs by Vst by 2 whole square minus Sn is half of that, which is VAT, velocity of the aeroplane, into t divided by 2 whole square. Alright. Therefore, we can, if we take t square by 4 common here, t square by 4 common here, we are left with Vs square minus Va square, or the velocity of the sound square minus velocity of the aeroplane square. Therefore, the height of the aeroplane must be root over of this t square by 4 into Vs square minus Va square equals to t square by 4. If you take out of the square root, then it becomes t by 2 root over Vs square minus Va square. Okay, so that's the formula for the height of an aeroplane which is moving with a velocity Va, considering the velocity of sound Vs constant throughout the medium. Alright. Okay, so that's how you can find the height of an aeroplane. Alright. Okay, so that's all for today's lecture. We will talk about some other properties of the sound wave in our next lecture. So see you in the next lecture. Till then, take care. Bye.